This clip is about FM transmitters, and I know there are nearly countless FM transmitter videos, like build your own FM transmitter, build your own radio transmitter, but trust me, you will be interested in what I have to show you. Firstly, I'm going to turn on my receiver and adjust it to the frequency. I think it was, no, it was somewhere else, it was like 90. So I have a simple FM transmitter here, and this FM transmitter is one of these Colbit's oscillator type. You can adjust the frequency here, and this one has a built-in microphone amplifier. Let me hook it up to a battery, and you will see that it will produce a signal at the adjusted frequency. And you can see already there that it is transmitting. I can see also that it's flickering. This is because I'm talking and the microphone is picking it up and it's over-modulating, but you can see it's basically working. Now let's hook up an antenna to this thing, because the antenna will greatly improve the range of the transmitter, and this is what we want, because let's just think you want to use this as a microphone. That microphone does transmit from location A to location B, and here you have it. It's not on the dial anymore, and if I change the frequency, you can see, it changed. And there is the frequency, and you can see it changes the frequency as soon as I hook up an antenna. But like I said, in our example, we want to use it like a wireless microphone, and like you build it into a housing and then you carry it as a microphone. And this antenna is waving around, and as it gets closer or far away from your body, it will change the frequency. Very simple solution for that, just add a quartz crystal. If you dig through various sellers, through their websites, you will find a crystal like this. It says 100 megahertz. So 100 megahertz crystal, which is spot on in the FM dial. And you can just add a crystal and get away with all this things like frequency drifted, even drifted just by putting the crystal there. And it would work. Well, that is how you may think it does work, but I can tell you it doesn't work that way. Once the crystal is cheating a bit, because although it says 100 megahertz, it's a so-called fifth overtone crystal. If you put it into a simple oscillator, it will oscillate at 20 megahertz. And there is a thing people do and did in the past, and you can make it that way, and this is how they did it. Here is the circuit for it, and this is a simple, very simple, crystal-controlled FM transmitter. Here you can see the crystal. A quartz crystal is wanting to hold the frequency it's been made for. For example, if you have a 20 megahertz crystal, it wants to transmit or oscillate on 20 megahertz. Stuck on, nothing different, 20 megahertz. But there is a trick. If you add a capacitor in series with the crystal, you can slightly change its frequency. For a 20 megahertz crystal, this would be like, instead of 20, 19998 or 20002. You can slightly change the frequency. And this is what the people are doing. They're adding a varicap in series to the crystal, which then gets fed the audio signal, and as a reaction, it slightly changes the crystal's frequency. There is another thing, there is more to say, because this is not what they want, because now they would have an FM signal on the very low frequency of 20 megahertz. But there is something about coils. Coils are frequency related. That means if you have a coil and you add a frequency, the resistance of the coil, the AC resistance, is going to be different. I have a drawing here. So you have a coil and you add a frequency, and you can see as higher the frequency gets, the more voltage you have on the coil. I have also numbers, and here it's with numbers. You start with 30 megahertz and they get around 10 millivolts, and then you go up to the FM band like 100 megahertz and they have 50 millivolts, 5 times more voltage on the coil than on the lower frequency. Based on this so-called high-pass filter, you can build your transmitter. People are even more smart and add a capacitor to the coil in parallel, and this forms a resonance circuit. With the resonance circuit, you can make a defined peak at a certain frequency, which depends on the value of the coil and the capacitor, to get out the signal that you want. And this is basically what people are doing. They are building a crystal oscillator, like let's say 10 or 20 megahertz, and then use a filter on the output and filter out the frequency they want. This is exactly what industry did, and here is the circuit or the board, and this is a crystal-controlled FM transmitter with a built-in microphone. Seems like it's one of these spy-bug transmitters, as it only offers you a microphone as audio input. Here you can see the crystal, the varicap, and here you can see a coil and a capacitor. Both are in parallel and form a so-called resonance circuit, which is tuned to the desired frequency. In this case, is 90 megahertz. I tune my receiver back to 90, and let's hook up my battery to the transmitter. I use these batteries because it works very well with these batteries. And connecting it the wrong way won't make it happy. Connecting it the right way, you see that we have a good signal. And now watch what I do. You remember me connecting my wire to the other board. And now let's connect an antenna to this transmitter. And the frequency stays exactly where it's supposed to be. I can touch the wire, I can touch the board. The frequency will not shift. It will stay spot on 90 megahertz in the FM band. Sounds simple, right? You can end the video, you have your crystal controlled transmitter and you have a microphone built in. For the volume, I have a low volume because otherwise you get a squealing noise and headphone users don't like that. Yeah, so this is my crystal controlled transmitter. I didn't build it, rather it was sent to me. But this is not your solution. Aside from some RF aspects of this thing, there are other aspects too. One of them, let's turn it, other aspects are the frequency deviation, or simply the volume. You can change the frequency of a crystal, and there is another effect that's in place here, the so-called frequency multiplying. You change the frequency 2 kilohertz on 20 megahertz, then on 40 megahertz it would be 4 kilohertz. On 60 megahertz it would be 6 kilohertz, and so far and so on. And so with these crystal oscillators you can make a FM signal that you can hear in the radio, but it's always going to be more silent than a regular station. For example, you tune in your transmitter and align the volume that you can hear it very well, and then you turn to a regular station and it's blaring out of the speaker because it's that loud. Sure, industry can build better. I've seen transmitters with crystal controlled oscillator multiplying the frequency and making a good volume like as loud as a regular station, but it's a very tricky and very much components requiring circuit that they have there. Industry has got an idea. I don't know why in times where you can buy PLL or DSP controlled transmitters, but some genius came up with a transmitter like this. This was sent to me, and based on the rust and the dust that's on the board, it's quite old. But it still works just like on the first day. This transmitter here, I got it and I tested it, made some tests with it, was curious about it. I figured out something's off with it. Because it's somewhere, when I tune the tuning slug, I get multiple reception points on the FM band, and something is really off with this. And then I figured out what is off with this. And like the crystal controlled transmitter, they built a transmitter where the oscillator is running on a third of the frequency what you're broadcasting on. Let's say you broadcast on 90 megahertz, you tune this one to 30 megahertz. And the advantage of the free-running oscillator is that unlike a crystal-controlled oscillator, you can make a very loud signal, a very strong frequency modulation. This one easily goes as loud as a regular radio station. Here's the schematic, and you can see how they made it. They have the oscillator here, and this is the coil with the many turns. This is this one. And the more turns on the coil, the lower the frequency. So this oscillator runs on like 30 megahertz, and here is a filter. And this filter, just like on the crystal oscillator, filters out the frequency for the FM band. Then it goes to an amplifier, and again we have a tuned circuit, coil and capacitor, allowing the FM band frequency to pass while suppressing other frequencies. In theory, at least. I did make measurements. And how did I make my measurements? Well, I took a telescopic antenna, let me get it, and I connected it on the output of the transmitter. Just let me get the other antenna, which is there too. Usually I don't want to pull it out completely because it's a bit broken, but usually people just pull out the antenna as far as it goes, as long as it goes, and then antenna is pulled out, it will work fine. No, it won't work that way. With these tuned circuits, you have a specific length. to get the impedance of the antenna right and match to the transmitter. And what I did is I put the transmitter on a non-conducting surface, connected this huge antenna to it. This is like 3 feet long or so. And then I started to pull out the element of it, like so. Of course, it was far longer, but this is just an example. So I pull out the element, and it's like on the meter I'm reading 7 bars. Then I pull it out a bit more, 9 bars. Oh, it's getting better. And pull it out even more. It went back to like 8 or 7 bars. So I defined a specific length of the antenna. Of course, like I said, much longer than this. This is just an example, but not the full length. At a specific length, I did get the most signal strength, and that plays into the cards of the transmitter, if you will, because most people would just hook up a random wire as antenna and throw it somewhere, which is not tuned, whilst I gave it a tuned antenna, giving it an advantage of its measurement that followed to get a good result. If you measure the spectrum of a transmitter, you want to have something that looks at least like that. I tuned for the middle of the FM band, and I got best signal there. And then I checked 196 megahertz, which is the first harmonic. This is how it's supposed to be, and this is how the transmitter is looking. You can see that there is a lot going on, a lot of unwanted frequencies. This is the frequency you want, do not want, lots of side frequencies. And how I measured it, I tuned this so the S meter is just about getting all signal bars from the reading. I tune it like that and then check the other frequencies so I get the most accurate reading. Then they came up with another transmitter, which I already plugged in as often the time is running out. 15 minutes is not a lot if you have a lot to explain. Okay, so there's the other transmitter, and it's tuned to 90 megahertz. And this one works on half the frequency, like they improved it from a third frequency to 50%. Now let's see why this is better. 19 megahertz, and this is freely adjustable. As you see, if I get my finger close to the coil, it detunes. But now let's hook up an antenna. And the moment I do that, if I get contact, the signal goes sky high, but the frequency stays the same. And this is just what I wanted to achieve. If they use a low frequency signal here and a high frequency signal there, connecting an antenna to the output will not affect the frequency of the low frequency oscillator, at least not much. But look, let me tune it to half the frequency to say I'm telling it's doing this and exactly like this. Half frequency, let's unplug the transmitter. And you can see it's really on half of the frequency. No, this is not overloading, it's an attenuator is activated. This really is broadcasting on half the frequency. And now, here's the spectrum. It's actually quite good. I mean, I think this is the one that has the most clear spectrum from these multiplying frequency transmitters. 49 megahertz, no bars. Still, I could hear the signal. Like it's in the static, I could hear it very clear, but not strong enough to get any bars on the S meter. 98, very strong. 2 meter amateur radio, not really a signal, just as the first harmonic. This one utilizes a low pass filter, which helps with filtering out higher frequencies. I then improved the gain of the receiver and got a very strong signal on half of the frequency, but still, it's very, very weak compared to the signal they want you to have. And based on how simple this transmitter is built, I'm really impressed with the results. And then, the other transmitter they built is this one. Keep in mind, like a red line going through all of these circuits, the red coil. And this one is their last or latest transmitter, and they just gave up with this frequency multiplying principle and just let it run on directly the frequency that you have. If you tune this to 100, it will transmit on 100. Here is the spectrum. Also, this one I think utilizes a low pass filter. I'm not sure, I haven't checked, I should have. Anyhow, this is how it looks like on my testing thingy. 98 is very strong, no other signals, and 196 is still there. It's not really strong, but you can pick it up. Okay, so I did another thing. I tested them for frequency stability. And what I did is I had I had a wooden thingy and I put it there so it is isolated from the ground and it doesn't get too hot. And then I checked which frequency drifts. I did it, 20 minutes warm up, 30 minutes, then measure frequency, let it run 30 minutes and measure it again. Winner is this one and worst is this one. But all of them are very well usable when it comes to have a transmitter that works with your radio. So these are the results. Very interesting frequency multiplying FM transmitter. Thanks for watching.